Thank you. So let's think about data assimilation a little bit. John covered a lot, and what we're going to talk about is where are the errors. That's intentionally a little bit of an ambiguous title, because typically in data assimilation we think of correcting errors in initial conditions or parameters. But there's a lot of simplifications that we make in the data assimilation problem that also introduce errors. And there's also observation types and density that introduce errors. So just starting in a general way, we want to look at all of those sources of errors and how they influence the results. So, we started with the initial condition problem, where there's solar radiation coming in, heating the Earth environment, and we can construct numerical models that represent the physics. So this is just an example of a 25th degree, what we call a free run ocean. It's forced by the atmosphere, but it's not assimilating data. And what you're looking at here is the surface eddy kinetic energy, and here's the same quantity inferred from historical drifter data. To first order, all right, there's lots of things that are very good about it. There's still a lot of work that needs to be done on numerical models when you get into the details, so I don't want to say it's all done. But to first order, we can reconstruct the statistics. The amplitude, the variance due to the mesoscale eddies, all of those kinds of things. That's great. This is not a boundary condition problem. So what is this? This is a Fukushima Daiichi off of Japan, and we were running an ensemble system at the time, throwing particles in to look at the density of particles moving off. An interesting question is, where would radiation disperse to over the area over a long time? That's not the question that we were trying to address here. In this situation, there were ships bringing in relief, supplies, aid, equipment. Ships take up seawater for cooling, for creating drinking water, and if a ship goes through radiated water, you've radiated the ship, it's now a large piece of scrap metal. So this was a direct application at the time, but the dispersion to a large degree is controlled by those mesoscale eddies. Those eddies are an instability process, which means a little perturbation makes that perturbation grow exponentially in time. So that perturbation or error can come from any of the sources of information we put into numerical models, which means after some time your model will still statistically have proper size eddies, proper amplitude, but they won't be in the right places, so we wouldn't be able to predict exactly where that material is going. So the purpose of data assimilation is to make continual corrections to the evolution of these forecast models, given all the information that we have. So what information do we have? Of course, all these wonderful satellite and in-situ observations. Hopefully we have a forecast from yesterday. Hopefully that forecast has skill at a later time. That's good information. Jean-Michel pointed out climatology has information in it that we can exploit. And then there's these ginormous numerical models that represent our understanding of dynamics. So what's the purpose of ocean data assimilation? Is to make a correction, taking all that information in to enable all these forecasts from global down to higher resolution scales. And so the first assumption up front is what are we trying to do? We want to make an estimate of what the whole Earth looks like given all of this information, and we want a minimum variance correction. That's our first assumption there. So we want something that deviates from all this information in a least squares sense. So fitting something to a line, we're estimating y equals ax plus b. We're estimating a and b by minimizing the square of the deviations to all that data. So it's very similar. It's a similar problem, but as we'll see, it's bigger. So let's formulate the problem up front. Let's just take a time interval to begin with. So we're going to say we're here right now, and we're going to take observations going back in time, and we're going to do a forecast, and take this as a long time interval. Don't restrict this at the moment in any way. And so we're going to build this state vector, and well, initially we're going to approach this from a whole Earth view, and we're going to say we're going to put all the ocean variables, temperature, salinity, velocity, sea surface height, over this entire time interval in here along with the atmosphere variables, land, ice, and wave variables. So how does this get set up? Well, as Julian pointed out, these numerical models are on nice discretized grids. And so initially we can represent all the initial condition parameters. A is a matrix that operates on this state. So this first row, if I'm setting the temperature at the initial time at this grid point to a value, this first row of A is all zeros except for one that's a value of 1 at the appropriate point and sets it to the initial condition. So if you look at the model code setting the initial condition, there's a row after row after row of setting all those initial conditions. All right. And Julian said the way these models step forward in time, they say u at time plus 1 is equal to u at the present time plus a combination of all the other variables in the model. So if we look at the dynamical equation in this first row, there's coefficients attached to u at time plus 1, all the other variables that associate it, plus whatever forcing there might be. And similarly on the observations, if we have an observation of temperature at some point, again, this is all zeros except for one value that's 1, and that's the observation. So we can take those little matrix forms there, put them together, and we know there's errors on these boundary conditions, errors on the dynamics, errors on the measurements, and we go to the mathematicians. We invite a mathematician in the room. We say, okay, we've formulated this problem. We want to minimize the square of all of these errors to all of these equations that we put down. The mathematician says, okay, I have derived this equation. The problem is solved. You're welcome. And they leave the room. The rest of us who are still in the room, we scream in terror. Why? This should be pretty familiar. This is a weighted least squares of fitting a line. Yeah, we've done that. I can do it almost by hand if I only have a few points. And these chords fall out, apparently. That one matrix, which is the weight, is the inverse of this covariance. Oop. Back we go. Okay. So this covariance matrix that John had talked about before, I'm talking about the same exact thing, little different point of view, no different. So why is this a frightening problem? Because Andreas Schiller last week told us what Godae's objective was to build a practical demonstration and feasibility of mesoscale forecasting. And as I think almost everybody has said, our computers are not big enough, which is why we started a global scale at coarse resolution and we nest and nest and nest down to higher resolutions that yet don't meet what Baylor says we need. And we do that because we cannot run the whole globe at the resolution that we want. So the computers are the limiting factor, so how big is this problem? So let's take, just for being concrete, a 16-day observation window and a 16-day forecast and a 1-minute time step, and let's ask how big is a whole Earth system. So we've been working on connecting together these different components, people in our group. So here's a 25th horizontal degree ocean. It has about 5 times 10 to the 9th variables at one time, with a 25th degree ice model, a T6180 81 atmosphere, and an 8th degree wave model, all coupled together. If I look at a 1-minute time step over this 16-day forecast with these systems, there's about 10 to the 14th variables. So this one vector with the ocean, atmosphere, land, ice, and waves is 10 to the 14th long. Okay, how does that impact the data assimilation problem? There's that vector again. The problem is that this covariance matrix, and I've blown it up a little, is 10 to the 14th by 10 to the 14th. And what's in here? This is all the information that explains how all the ocean variables relate to one to another. This is all the information of how all the ocean variables relate to all the atmosphere variables. Ocean to land, ocean to ice, ocean to waves. So it's at the limit of present technology for a prediction system to be able to do this numerical integration and produce those 10 to the 14th variables. So now we've got a problem that's a factor of 10 to the 14th larger than what we can do feasibly right now. Okay, it's too big. So what do? We make assumptions. If we waited about 100 years and assume there's doubling of computer capacity every 2 years, sometime 100 years from now we would have something big enough to be able to solve this problem directly. If Baylor's estimate is that we'll have direct numerical simulation in 2200, that would give us about 10 to the 40th variables. And so we can expect direct numerical simulation, data simulation, somewhere around 2400. And I've probably seriously underestimated that. I find over time, all our estimates of when we'll get something done are horribly optimistic. And I'm not patient enough to wait for that. So, we're going to do something now. We're going to make assumptions. First assumption, we're going to assume all of these blocks off the diagonal are 0. What does that mean? That means corrections to the ocean are not related to corrections in the atmosphere. Chris Harris just showed some good examples, and Mark Barassa talked last week, that say, if I change temperature near the surface of the ocean, that changes the fluxes and what happens in the atmosphere. This assumption is completely wrong, but there we are. I'm going to assume that if there's observation of rainfall that changes the hydraulic routing in a land model, that changes river outflow, that changes ocean salinity, I'm assuming that's not connected. If I assume that I observe ice and I put it into the ocean, into a coupled system, this happens to us all along, without correcting the ocean, the ice melts. So by setting this to 0, that's what's happening right now. And if Tony were here, he should be well justified in being furious that we have destroyed all his observations of ice by not including this. And similarly with waves. Fabrice can tell us how turbulent mixing of the surface waves change the mixed layer depth and all these problems. Okay, so we've introduced errors right up front. So, all right, but what this means is that I can independently do the inversion of each of these block matrices independently. So, okay, all you oceanographers, all you meteorologists, land and ice and wave people, go to your own independent science communities, work on data assimilation on your own. Oh, thank God, it makes it easier, but at least we're aware of what we've done. So let's blow up that one block of the ocean. So again, this is all the ocean variables over this time period, and I've just listed 5 time steps, all right? So how big is this? Well, the sad thing, whether it's good or bad, I don't know. What fraction of the whole Earth system prediction problem is the ocean? It's about 80 to 90%. So throwing away the atmosphere and waves and ice really hasn't reduced the problem significantly. So the problem is pretty much just as big as it was before. So we're going to have to make more assumptions. But before you make assumptions, let's take a look at what happens in the ocean. So here's a couple of areas. This is in the Gulf of Mexico. That's the Mississippi River Delta. That's a bit of Florida. This is a 3-kilometer model covering the whole Gulf. And these are surface drifters that were released at the beginning of 2012, no, July 2012. And you can see the correspondence between the model and drifters, which is good. But if we ask, what should we be correcting? The initial conditions are a big source of error. The surface boundary forcing, you can see these guys are following geostrophic flows. There's Hurricane Isaac that goes through here, and you see, yes, they respond. If you recall the animations from last week at high rate of the atmosphere jittering on top of the ocean, it's a turbulent input to these big eddies. The atmosphere doesn't drive those. Lateral boundary conditions, we've pushed the boundary conditions out beyond the Straits of Florida, beyond the Yucatans. That's not a problem. Dynamics, we say, gosh, modelers, you guys have done a great job. We don't have to worry about errors there. This is a similar example. It's just up here in the Mississippi Bight. And this is a 1-kilometer resolution model that covers the whole Gulf of Mexico. And again, these are just surface drifters that were deployed during that time. And what you can see is the surface boundary condition is a real strong driver of what happens here. Wind goes through. You can see the response of these drifters just sailing off. What that means is that the initial condition information is lost pretty quickly. A short period event from the atmosphere wipes away with the initial condition. Lateral boundary conditions, well, we've removed those. They're far away. And the dynamics, sure, there's problems with the dynamics. But in the end, what has been the focus for the operational oceanography community is this, the initial conditions for the ocean mesoscale. So how should we look at solving this problem, which is still enormous. What assumptions are we going to make? First, we're going to make corrections not at every model time step, but at just specific times. So Jean-Michel said they make corrections every 7 days. We make corrections once a day. So just for illustration purposes here, I've shown making corrections only at 3 of these first time steps. In reality, if I'm making corrections once a day, these are about 1,000 elements apart. So making corrections infrequently reduces the size of this problem huge. Okay, the second assumption is that I'm going to assume that the dynamics are correct. You know, up front when we formulated the problem, we said there's error to the dynamics, and the dynamics are part of this whole block here. So all I've really got to do is make a solution, invert this one little block, which is just the number of ocean variables at one time. So the problem's much smaller now. And by doing this, basically, what we've derived is a cycling 3D var. So how do you solve this problem? You make an estimate of what the correction is at this first time. You've assumed that the dynamics are correct. So you integrate forward in time to the next block. You make a solution at that block, and on and on. So those are the basic assumptions that go into what we've done. Great. We go back to the mathematician, invite him back. Come on over. We've made some assumptions to try to reduce the problem. Given those assumptions, can you formulate a solution? The mathematician says, yes, I've derived this equation. The problem is solved. You're welcome. And they leave the room. We all scream in terror again. Why? And it goes down to this background error covariance. Here I've put a subscript of B on it because it applies only at one time. So one way to understand this, suppose you have one observation, just one observation. That means Y here is a single value. H, as we said, selects one component of the model at that observation location. So it's a long vector of zeros with one element set to 1, and you have some forecast from yesterday, and you get the difference between the observation and yesterday's forecast. When you look at this operation, basically it's selecting one element of B, which is the error in the background at that observation point. Great, it's a single number. R, since you have one observation, is a single number. It's the observation error. I can add 2 numbers by hand. Okay, I might need I could take an inverse on a slide rule, and I can multiply 2 numbers on a slide rule. So this all boils down to just a single number. But what happens here? Okay, H is a long column vector that has one element 1. It's going to select one column out of B. That column describes how the information at that observation location is correlated to all the other values in the ocean. So if I observe sea surface height at a location, I need a column in here that says how temperature, salinity, velocity is related to that sea surface height throughout the water column at that location, at all the surrounding locations. There's just never enough data to actually determine what B is. And so that's where all the exciting discussion happens, is how to specify this covariance. How do you specify all the information that goes in there? There's different approaches. Some people use analytic forms. Coding those is numerically efficient. One of the big considerations in specifying B is that you want it to adapt to the local conditions. So if I know I'm in an eddy versus outside of an eddy, the relation of the vertical temperature and salinity structure is going to be very different in those two situations. So there's some benefits and drawbacks to these. Using historical observations, there's no model bias in historical observations. But this is 10 to the 9th by 10 to the 9th. We don't have that many in situ profiles to make confident statistics. So there's rarely sufficient data that can actually go with this approach. There's prior model results. We can build an ensemble OI. Run along integration of a model, and from that long time period, just build up that whole correlation covariance matrix. Ensemble Kalman filters. I'm going to take an ensemble set, and right now, I'm going to compute all the covariances from that ensemble between all the variables and all the points, and it captures the present state, whether I'm in an eddy or not. But what it suffers from is a small sample set. How many samples number of ensembles do we really have? So this is obviously an area of active research and how to properly specify that. So given all of those things, what is feasible now? So this was a reanalysis during this experiment. You can see a lot of the features that these drifters follow are reconstructed in this little ocean model. That was Hurricane Isaac. But you notice this is a Gulf of Mexico hindcast at 3-kilometer resolution, and this was experiment B6. So it took a little while to get this reanalysis straight, and the reason for that is what we initially saw. So Javier Barón Vera at University of Miami took a VISO, gridded maps, computed geostrophic currents, and constructed Lagrangian coherent structures, and superimposed that on some nice satellite imagery at the time that showed this nice advected chlorophyll plume going out, which matched up with the LCS structures. And you can go to the satellite altimeter data. This is a 35-day composite of sea surface height anomaly. And so you can see this low feature right in here, which of course is what a VISO comes from. The problem was that when we looked at the model results at that time, Javier computed the LCSs from this Navy coastal ocean model and from HICOM, and they were both just completely deficient in representing that feature. So here was the data. The data contains that feature. Here's data assimilation. Here's two different dynamical models that both use the same data and the same data assimilation that produced the wrong result. So where's the problem? It's in here. So we went through a whole long list of experiments I won't bore you with. But there were a few experiments that really showed how paying attention to that covariance matrix is important. So I'll talk about those a little bit here real quickly. But the result is, here's one of those experiments after tinkering around with the covariance matrix, reproduces that feature much better. That's the change that really worrying about the data assimilation can make in these kinds of forecasts. So the data assimilation matters, those covariances matter. So what were some of the little details of the issues? So what we're looking at here is the background error covariance that describes the temperature error at 200 meters depth, going from August 21st, 22nd, 23rd, 24th. So we were doing a data assimilation cycle every day. This is one formulation of the background error covariance. This is a different formulation. And you can look at the temperature ranges on this and realize that the background error covariances in this are much larger. You can see these lines where the errors are low. Over time, the errors increase. That's what it should do. You can see places where the errors are large and then satellite data comes in and it gets reduced. So it needs to account for how the observations are changing the errors over time. So we can't construct a covariance matrix for this problem from scratch, but we can use observations to determine which of these two covariances are more realistic. So we can take the observations minus the background. That is, every day we have the forecast from the prior day. Let's just difference that from the observations. And we can look at what the errors are over depth. That's an estimate of what the background error covariance is. Sampling these two representations at the same observation locations and averaging over time, this is R1 and this is run 2. And you see run 2 is a much better representation of the background errors. And you can also tell that run 2 had lower temperature errors. So that's a positive step. So the thing that doesn't show up, does it? No, it's hard to see. Oh well. This is a controversial point, and I think it was asked, and there's been a few examples today, of why do we use data over long timescales? So a couple of the experiments, R2 used data that was available just in the last 24 hours. So here's a satellite track on one day, it corrects the model. This is the correction in temperature at 200 meters. The next day, nothing, but different satellite data. So every day, it's only using the newest data. This run, we took the satellite data and we said, use all the data over the last 5 days. So you see this track over here. On the second day, it gets used again, and on the third day, and on the fourth day. And you can see it's making consistent, structurally consistent, and smaller amplitude corrections every day. And if you could see this little blue line here, you could see that the errors in the results from this run are significantly lower than the errors using the data only once. So in meteorology, if you get these error lines to change by a line width, that's reason to have a celebration. Oceanography, we've not been doing this as long, so we can still get fairly sizable jumps. But we get this reduction in error by doing this, and in theory, we're not supposed to do that. But we can look at different Godae systems and look at what the cycle interval is and look at how much data is used over time. And it's pretty consistent. People have found using a long time period of data gives better results. So in the end, this is a proof by contradiction. We have this result that contradicts theory. Theory says we should only use data once. If you use data more than once, you're doing the wrong thing. But the result is using the data more than once provides a better result. So proof by contradiction, what does that mean? That means one of our assumptions that we made before is wrong. So which assumption was that? Let's go back to this matrix here, where we said we're going to assume all these things are zero out here. We're going to assume that the errors or corrections at this time are not correlated to the errors or corrections at this time. So we've limited the influence of the observations to be just at one time. Typically, when people work on building these covariances, the first starting point is that you assume, well, the structure of the covariances is very similar to the ocean features themselves. So what are the spatial scales? The size of eddies. What is the vertical structure? Oh, it kind of looks like eddy's vertical structure. And therefore, what should the time scale of corrections be? It should be time scales of features in the ocean, eddies, a week, something like that. So some of these assumptions have really limited what we've been able to do. So we went back and we said, okay, those assumptions got us to a 3D VAR. What if we try emulating a 4D VAR? That is, corrections from one day's analysis can influence the corrections on another day's analysis. So here's what we did. We have every day an analysis that uses the prior 1 day of data. So the data only gets used once. But we take that analysis and we just divide it by 5. And then we use the analysis from the last 5 days, add them all up, and that's the correction that gets applied every day. So, for example, this is from one of the experiments using the full increment. Here's the analysis divided by 5 on 1 day. The previous 5 days of analyses are all added up, and that gives us the correction. And I won't try to explain the PDFs here, but that experiment where we tried to emulate that 4D VAR turns out, yeah, the PDFs change pretty significantly, and it has the lowest errors relative to all of those drifter observations. Okay, so we said 3D VAR is limited because of some of the assumptions that went into it. So we go back to our mathematician friends, and we say, we assumed some things, maybe we should back off those. Can you help us solve this problem? And they say, yes, I have derived this equation. The problem is now solved. Thank you. And they leave. Leave us with this equation for 4D VAR, which basically the difference is we have this extra operator D, which is the dynamics. So when we originally formulated the problem earlier, we said there's all these dynamic relations between variables. Well, it's back. So we said we can understand what this does by looking at just one observation. And we see that this provides one column of the B matrix, which is the correction that gets made. We can see a little bit of what the 4D VAR does by doing the same thing. Let's take one observation, and we can look at this operator here to get an idea of what it's doing. So here's an example. So John and others have said this dynamic operator, the background error covariance, and the dynamic operator transposed, that's the adjoint. How do you transpose a numerical model? It's tricky. We're going to take one observation, and the first thing we do is invert this operator, and here's the inversion of that going back in time. So time is back in the problem now. Before in a 3D VAR, we were just constructing a correction at one fixed time, but now we have an observation at time 0, and this operator propagates it back through the dynamics 4 days earlier. Then we invert these two operators. D is just the model, so we can integrate it forward in time. And here's the result. Here's the correction we should make to our system based on a sea surface height observation. And I hope everybody looks at that and says, that's completely nuts, right? Why? Why does this look like just noise? It's because this dynamical operator doesn't discriminate. So I observe sea surface height here, and it's different from the model. How many different ways can you think of to make the sea surface height in the ocean higher? So I can change the thermal structure, expand the water column. That's one way. I can make a tsunami a mile over there, traveling at 300 miles an hour, that rise right here, right at the observation time. Or a tsunami further away. I can make a huge convergent wind that blows the water together and mounds it up. To the dynamics, those are all equally plausible solutions. It doesn't care. We look at that and say, you know, that's not in my experience that tsunamis are the typical sources of errors in these predictions, or that there's these massive hurricane force convergent winds going straight up. No. So we have to put a little thought into B again, and basically some of the dynamics in there, like conservation of mass, there's no error to that. I don't think there's an error to conservation of mass, even the way it's formulated in a numerical model. So if you set some parts of B to 0, you get a much more sensible solution from a 4D var. So I'm going to show you an example of 4D var assimilation here in a minute, but we've gotten to this point. Those are simplifications that go into the data assimilation process. They're assumptions that we all put in there about how different variables are related to one another, and we're forced to do that because the problem is darn big. So here's another drifter deployment, 2016. So 4 years later after the 2012. So instead of 200 drifters, here's 1,000. This is done by the folks at University of Miami, University of Washington, UCLA, a whole lot of people. So you can see the forecast system we had running at the time, that we included a lot of what we learned in it. You can see the drifters following the loop current, a lot of the other structures, but watch this mass of drifters over here. You see the loop current going up here, and they ignore the model. That's rude. You see these guys caught in this cyclone? The model has a cyclone there, but watch the model cyclone. It kind of gets off, but then it just kind of jumps over to where the observations are. And then it gets off a little more, and you can see that guy just take a big jump over at that time. So these drifters were not assimilating them in the model. So what's causing these kinds of errors? It's basically the density of data. So here's February 26th and February 29th. There's the model state on February 26th. And you see on February 29th, it's flattened out, and the northward extension of the loop current's been moved back about 100 kilometers. So what did that? Well, we looked at all the satellite data between those 2 days, and it was basically this set of ground tracks where the front was observed right across here, that pushed it back down. Here's another example where the position of the model cyclone was off by an order of 100 kilometers. This is all the data that we had between March 10th and March 16th. So over a week's time, we got one observation, which just by luck happened to go through that eddy and push the model back on track. Here's this other example going from March 20th to March 27th. So another week, we got real lucky in this case. You can see how far out from reality the system is. We have a flow that's going basically southward. This shows a big westward and then eastward flow circulating cyclonically. So all that altimeter data comes in and corrects the model to put that eddy in there. So a large part of the errors are also due to just the amount of data that there is for the ocean. If we had full observations of the ocean, 3D, at a high frequency, nobody would care about this covariance operator. All it would have to do is smooth the errors out in all the observations. It wouldn't matter. But the fact that we have so little data in the ocean, It tells us how every observation is related. It extends the influence of those observations to the subsurface. It extends them spatially. That operator is the main part of the data assimilation. So, where's the future? The future is in fronts. So we took our model and we threw a bunch of particles on it and we integrated them over time. And you see these lovely structures starting to form around the eddies. You go back to fluid dynamics equations and you look at the evolution of concentration of a tracer, and it says if you have a non-divergent flow, ocean's non-divergent, that the concentration of a tracer should not change in time. But here we're seeing concentrations change. That's because these particles, we put them just at the surface, they're buoyant, and all they're seeing is the surface flow. So this goes back to what Baylor had mentioned. Along these fronts, there's a secondary vertical circulation that's driven by the water masses being pushed together. That vertical circulation, when it hits the surface, creates a divergence and a convergence. So that's why you get these changing densities around the fronts. How well can, oh my God, where have I gone? Okay, back on track. How well can we do predicting fronts? We can set up an experiment. We did set up an experiment, and we wrote a paper about it. So we set up an observation system experiment from 2004 to 2005, a year and a half when there were 4 satellite altimeters available. And we set one experiment up where we assimilated everything and said, there, that's our best result. We'll call that nature. And then we went back and ran a whole lot of permutations of different combinations of satellite altimeters from none up to 4. And we were able to take those experiments back next to nature and say, okay, what's the spatial anomaly correlation of different properties averaged over time, and how do they compare? So with no altimeter data, you get spatial anomaly of these different properties from steric height, mixed layer depth, surface divergence, and Q1, which is the omega equation forcing that we saw last week. That's the frontal forcing. Basically, you need an anomaly correlation better than 0.6 to claim to have skill. So no altimeter data, no skill in anything. Okay, we can save computer time and stop whining about computers if we don't have altimeter data. Add one altimeter satellite, and we ran different experiments of TOPEX, JSON, ENVISAT, GFO, and you get an anomaly correlation of steric height that jumps up 0.85, 0.9. And why is that? Okay, here's an eddy that's 200-300 kilometers across. If I have that thing mispositioned, that's not going to mess up my anomaly correlation terribly badly. So as you add more altimeters, you get an increasing anomaly correlation. The hard part is convincing people that going from 1 altimeter to 2 altimeters is worth pushing this up by 0.03. But when you look at what's happening around the fronts, the frontal forcing and the divergence, that creeps up fairly linearly until you're at 4 satellites, which means right at 4 satellites, you almost have skill in predicting the frontal processes, getting the fronts in the right place. So do those things exist in the real world? So here's a snapshot of mixed layer depth. That's a satellite snapshot of seaweed. I don't know how they retrieve that, but there we go. It shows where there's sargassum on the surface of the ocean, and you can see it's been pulled together in all these nice little structures wrapping around lots of little eddies. The mixed layer depth, where it's very shallow around here, that's the upwelling due to the frontal processes causing that. So you can see in this model prediction that's assimilating all the data, it's getting the loop current generally in the right place. The exact positions of the front are off. You can see all these little cyclones and anticyclones wrapping around the shelf break. They exist in the real world. You can see the frontal process effects. They exist in the model, but they're not in the right place at the right time. There's just not enough data to try to constrain those things. So here's happens to be a data set. What if we were to use this data set, extra data, to try to constrain a system and see what we can produce? So here's an example of 3D VAR assimilation, not using the drifters. And what we're comparing is the model forecast, that purple line of the drifter trajectory, to the actual drifter trajectory. Getting forecast trajectories is really hard because once your trajectory starts going off, it doesn't come back. The errors just get bigger and bigger in time. If you take the 4D VAR, assimilate those drifters, up to a certain time and then make a forecast from the 40var of those drift trajectories, you get really nice results. We've never gotten anything that good before. So these little observations, they're simple drifters. They're basically code type drifters. They're cheap. They're like $800. You can throw out 2 of them. They're persistent in the area you care about. So if you have some kind of high interest local event and you're wondering what the ocean circulation is, this is a great way to do it. Because what are they doing? They're acting like little altimeters. If the currents are geostrophic, they're measuring the sea surface height gradient. So they're all there in the features you care about, reporting all the time. It's not just one transect across real quick. There's SWOT. Uh-oh. It's lunchtime. Here's an osseous SWOT. We ran one model. We sampled it with conventional and SWOT altimeters. So here's the nature run. Here's 2 runs after assimilating those. SWOT, you get the features and fronts much better. Go SWOT. There's sub-mesoscale, so there's a 250-meter resolution model. The thing with the sub-mesoscale, here's the sea surface height, the Laplacian of the sea surface height, which is geostrophic vorticity compared to the actual vorticity. So the sea surface height reflects those sub-mesoscale features, but the dynamics in those features are very different from what we've seen in mesoscale features. Mesoscale, due to changes in the thermocline depth, they're geostrophically balanced, they're this big. Sub-mesoscale, they typically don't go down below the mixed layer, so that's surface vorticity and 200-meter vorticity. They are advected by the larger scale, so the dynamics of them, now we have to worry about how they are being moved by the large scale. So kind of the approach we're taking on this is first correct the mesoscale, which is steering currents for the sub-mesoscale, and then implant the sub-mesoscale features that get observed by SWOT. So it's getting towards hurricane forecasting. Okay, last slide. The problem is, when you look at sub-mesoscale, everything we've assumed and developed about data assimilation, you basically have to throw out the window. It's all predicated on assuming we're doing mesoscale eddies that are large scale, long time period. And when you apply assimilation to all these other problems, trying to reduce errors in barotropic tides or internal tides, or assimilating wave gauge data to correct wave boundary conditions, or constructing fluxes, or in these couple of systems, you've got to just almost throw away everything you have, go back to the basic assumptions, and rebuild the whole problem. So the good news is that you're here. You're here to fix all these things that we screwed up in the past, and you get to clean up the mess. That's an opportunity. So I'm going to end at that.
Questions to Gregg?
No, it's lunchtime.
Jerome?
Yeah, well, Paul, a naive question. Why do you time step every minute? What is the driver?
That's a numerical model requirement to maintain stability of the numerical system. So the time step is dependent on the resolution of the model. Typically, when you cut the resolution in half, you also have to cut the time step in half. So the number I put there was basically for the global 25th degree model. When you go to that 250-meter resolution, the time step goes to a few seconds.
Okay. Brian?
Just say it.
Oh yeah. Will we see improved fronts from SWOT and from the simulations that we've done? I would say, yeah, we will. We should see this compared to what we can do now relative to what truth might be. So for the mesoscale, at least, the initial tests show that SWOT's going to be a big jump forward. There's lots of potential there. Right. So why such a big jump? Is because these are single points along the ground track. You know, that's a swath. The amount of data is about 2 orders of magnitude larger. And if you look at those lines cutting through these eddies, you hit the edge of an eddy and you poke it a little bit with the assimilation, and very quickly that little poke that you put in there gets washed away. So you don't have the opportunity to get the spatial structure of the eddy right with just that altimeter data. Yeah, you can get the general eddy in the right place, but getting the shape of it and the whole structure is really hard.
Okay, something else? John?
Greg, when you assimilate the drifter data, are you treating that as a time series of Eulerian velocities or something more sophisticated?
No, it's that crude. We take successive positions of the drifters, and I believe the time interval was on the order of 6 hours that was used, and just inferring velocity from those successive positions. But fortunately, they report every 15 minutes. So there's, given the GPS positioning noise and the reporting interval, the actual inferred velocity error isn't that large, usually.
Other question? Yeah.
So, and we used to assume that the observation errors are uncorrelated.
Oh yes, that's wrong.
Yeah, but with the new kind of data like SWOT or other satellite,
Yeah.
maybe in the future you can change this kind of approach.
So you can find studies that people have done looking at correlated errors in present altimeter data. And I think some of the folks at CNES have done this because we know there are long wavelength errors due to orbit errors, atmospheric corrections. So there are correlated errors on the ground track. And I think Pierre-Yves last week pointed to some of those. And so it wasn't quite as obvious at the time. But there is work. And if you look up correlated errors in altimeter data, you can find some papers on that.
Thank you.
Okay. Something else? No? Okay, thank you again, Greg.